In this video, I'm going to show you how to train gradient boosted tree models with Skytree. Skytree gradient boosted tree models are invoked by specifying the GBT option after the Skytree server command, and the option names are specified right after that. To see a list of the available options and quick descriptions of all the possible options, we can just type Skytree server GBT --help. So let's do that and take a quick look at the possible options. So there are a lot of possible options, and we see that quick descriptions of all the options are printed out. So this is a really quick and helpful way to remember the syntax of all the options and the default values. So instead of opening the user guide, you can just type --help after any one of the Skytree modules. Actually, it doesn't have to be GBT, and you will get the list of all the options and their quick descriptions. So let's begin with a simple run that trains a GBT, gradient boosted tree model with Skytree. In this command, we specify the file that has the training set by using the training in option, and we specify the file that has the labels for the training set by using the training labels in option. We pick the number of trees, and we pick the file that we're going to write out the model in. We're also using the Linux T command to write out the log that's printed out during the run into a file as well. So we will both see the log being printed out, and we will also write out the log into a file. So let's give this a run. And the run is finished, so we can open the log file that we wrote out. So we see that Skytree begins by printing out some basic system information. And after that, we see that the exact command line arguments that we typed are printed. And this is a common thing with Skytree. With any given run, Skytree is going to print out the exact command line arguments. And after that, we see some system status information. And that's followed by the options that are used in giving this run. So some of the options are things that we have specified, like the number of trees and the training data. And some of the other options are not something we have specified explicitly, but they have default values, so Skytree is using those default values for those options. So let's go down in this file. We see that after this information, Skytree starts training the model, and we see some progress information. And finally, Skytree tells us that the training is done, and the model is saved, and it reports the total memory that was used. So now that we wrote out the model, we can use that model to make predictions on the test set. And that's the next thing we're going to do. We're going to specify a testing set, and we're going to specify the file that the model is in. And we're going to specify the file name where we want to write out the predictions. And giving this run, Skytree is going to read the model and read the test set and make predictions and write out the predictions. So let's run this command to make predictions on the test set. So let's open the predicted labels that we wrote out. So these are the labels that were predicted by Skytree. And using the Linux paste command, we can compare these to the true labels. So on the left column, we see the predicted labels, and on the right column, we see the correct labels. And we see that many of them are predicted correctly, but some of them are predicted incorrectly. So in the previous run, we wrote out the predicted labels, but we did not write out the probabilities that were estimated. And gradient boosted trees can actually estimate probabilities for the classes. So we can write those out too by using Skytree. And to do that, all we have to do is specify the probabilities out option and give a file name where we want to write out the probabilities. So that's what we're going to do next. So let's open the probabilities file that we wrote out. And we see that these are numbers less than 1 and greater than 0. And these are actually the probabilities for each data point belonging to class 1. By default, Skytree uses a probability threshold of 0.5 to make the predictions, the label predictions. But that is a parameter that can be changed by the user. So if we want to assign the labels by using a probability threshold of 0.8, we can do that by specifying the probability threshold option. So this run that we're going to give is very similar to the previous run. We're again specifying the model file and the test set, and we're writing out the labels to a labels file, but this time we're specifying the probability threshold to be 0.8. So let's take a look at the predicted labels together with the probabilities that we predicted. We're going to use the Linux paste command to print out the probabilities with the labels side by side. We see that since we use the probability threshold of 0.8, only the points that have probabilities greater than 0.8 are identified as class 1. So these probabilities are probabilities for being class 1, and the threshold we specified is also the threshold for being identified as class 1. So with gradient boosted tree models, we typically tune over various parameters like the number of trees, the learning rate, or the number of splits. But we just gave a simple run with a given fixed number of trees and we didn't tune any of the parameters. So let's next take a look at how to tune parameters with Skytree. And this can be done in 3 ways. We can either use k-fold cross-validation by specifying number of folds using the num-folds option, or we can use a random holdout set from the training set by specifying the holdout ratio, or we could use a specific file where we keep the tuning set by specifying the tuning in option and giving the file name. So let's next give this run where we tune over various parameters. Let me quickly go over the options that we're specifying in this command. We specify the training file and the file where the training labels are in. And after that, we specify the number of trees to tune over. So in this run, we're not specifying a single number of trees, but we're specifying a range of numbers. This notation simply means that we're going to start by 10 trees and go by steps of 20 all the way up to 90 trees and just try these different numbers of trees and evaluate them. We're also tuning over the maximum number of splits while we're building all the trees. And once again, we're using the same notation. We're starting at 2 splits and we're going all the way up to 6 splits by steps of 2. So we're going to try 2 splits, 4 splits, and 6 splits. And we're also tuning over the learning rate, and in this case we're specifying the learning rate to be 0.05, 0.1, 0.15, and 0.2. So this is again using the same step notation. So we're specifying a holdout ratio of 0.3, so that means Skytree is going to take 30% of the data set and put that aside during tuning, and for each combination of the parameters that we specify, it's going to evaluate the accuracy by using that 30% holdout set. We're specifying our testing objective to be accuracy. So when we're tuning over different parameters, we may want to maximize different notions of performance. So in this particular run, we're specifying our testing objective to be the accuracy. So that's simply the fraction of the correct answers predicted. And in the same run, we're also specifying a test set. So what Skytree is going to do is it's going to tune over these parameters that we specify. And once the tuning is done and the best model is found, Skytree is going to read this test set and it will make predictions by using the best model that it has found by doing the tuning. It's also important to note that while doing the tuning, the training is done only by using the 70% of the data set and evaluation is done by using the 30% of the data set. But once the best parameter combination is found, Skytree is going to use the full training data set to train the model using that best combination. And the predictions for the test set are going to be done by using this final model that's trained on the full data set. And as before, we're also specifying files to write out the outputs, such as the probabilities file by using the probabilities out option, and the labels file that we want to write out using the labels out option. And we're also specifying a file for the tuning results. So the tuning results out option gives the file name where we will write a tabular form of the tuning results. And finally, we're also writing out the model, which will allow us to use this best model that we find for making predictions on other data sets. So next, let's give this one. So we see that Skytree is trying multiple parameter combinations now and evaluating each one of them. And once this is done, it will record the best model found and it will write out the outputs for that best model. Okay, so let's open the log file that we wrote out to see what has happened during this one. So we see that, as usual, Skytree begins by printing out some system information, and right after that we see the usual working directory and the command line arguments, and right after that we see the system status information, and after that we see the parameter combinations that were specified. So we use the colon notation that specifies a uniformly separated list of values, and Skytree interpreted those and it just lists all the unique values that we have specified. And for certain options that we did not specify, Skytree just uses the default values. So as we scroll down in this log file, we see the list of parameter combinations that are going to be tried. So we gave lists of parameter values, and Skytree is going to try every single cross combination of these parameter values. So we see that there's a learning rate of 0.05 coupled with the maximum splits 2, and then we see the same learning rate 0.05 coupled with maximum splits 4, and then the same value is tried for maximum split 6. So each combination of the parameter values that we specified is being tried. One perhaps curious thing is that the number of trees doesn't change in this list. It's fixed to 90, and the reason for that is to try 10 trees or 30 trees or 50 trees, Skytree doesn't need to start from scratch, because on the way to building 90 trees, you actually have to first build 10 trees and then 30 trees. So while Skytree is building these 90 trees, at the points where we specify the 10, 30, 50, and 70 trees, it actually records the performance for that number of trees. So that's why those numbers of trees are not listed in this tuning parameter combinations list. So as we scroll down, we see that Skytree actually starts trying each one of those tuning parameter combinations. So there are 12 of them, and we see the progress report for the first combination. And as we quickly scroll down, we'll see all different combinations being tried. And finally, after the last parameter combination is tried, Skytree reports the best tuning results for various metrics. So here we start by seeing the best tuning results for the Gini metric. And as we go down, we'll see the best tuning results for other metrics as well, like capture deviation. And the precision at K is another metric. And the F-score is another metric. But the one we're interested in this particular run is the accuracy metric. So let's just go down and look at that. So even though we specified accuracy as our testing criterion, Skytree actually reports all these other metrics as well. So here we see the best tuning results sorted according to accuracy. And right below that, we see the tuning parameter combinations for those best tuning results. So the best accuracy that was found was 0.872793. And we see the parameter combination for that best accuracy result to be the number of trees 90, the maximum splits 6, and the learning rate 0.2. As we go down, we see a few lists of options. These are the exact options we would need to specify if we want to reconstruct the models with the best performance according to various criteria of performance. So we're interested in the model with the best accuracy. So we see the exact options that would allow us to retrain this model with the best accuracy. In addition to the model options like the number of trees and the maximum number of splits, there are also options specified here that give us the random seeds. So Skytree uses some randomization, and if we want to train the same model from scratch, we would need to specify the same randomization, so Skytree is printing out the random seeds that we need for that. And finally, let's note that Skytree also tuned over the probability threshold. The default probability threshold is 0.5, but when we're doing tuning over certain parameters, Skytree also tunes for the probability threshold, and it reports the threshold that would result in the highest accuracy. So up to this point, Skytree was trying these parameter combinations and finding the best ones. And next, what it does is it trains a model on the full data set. So instead of using a holdout set to evaluate and training only on the 70%, it now trains a model on the full data set by using the best combination found. So because we specified accuracy as our test criterion, Skytree is training using the options found for the model with the best accuracy. So once that's done, Skytree actually uses that model to obtain predictions for the test set that we specified. And finally, Skytree writes out the model into a binary file, and it reports the total time taken and the total memory used. Let's next open the tuning results file written out by Skytree and take a look. This is a simple comma-separated value file that contains all the parameter combinations that were tried, together with various measures of performance for the corresponding models. So the first 10 columns or so have the parameter values that were tried, such as the number of trees, the maximum number of splits, and the learning rate. And since we did not specify all the parameters, we did not tune over all the parameters, some of these columns actually consist of missing values, which is indicated by successive commas. The next few columns have various measures of accuracy for these parameter combinations, such as the genus score, the F-score, or the classification accuracy. And the final few columns have probability threshold values that one would use to obtain the best performance according to various criteria. For example, if you would like to maximize the classification accuracy or the F-score, you should use the probability threshold values reported in the appropriate column. As you can see, there's some overlap between this tuning results file and the log file that we have just inspected. The tuning results file has a nice tabular format that makes it easier to read using various software tools. And it's also more complete in the sense that it lists all the parameter combinations instead of just the top 10 in accuracy, which was the case with the log file. Many real-world datasets have a significant degree of imbalance. For example, if we're trying to develop a system for detecting fraud in credit card transactions, our training set will contain many more non-fraudulent cases than fraudulent ones. With such a high degree of imbalance between the labels we're trying to predict, straightforward applications of machine learning methods may not result in the desired degree of accuracy. There are various methods for dealing with imbalanced datasets in Skytree, and we will start with the simplest one, namely using the -- imbalance option. And this can actually be quite effective. Here's a simple run with the -- imbalance option. This is quite similar to the runs we gave before, so let's quickly go over the options we're using. As before, we start with the GBT option name and specify the files for the training inputs and the training labels. We won't be doing tuning for this particular run, so we just pick a specific number for the number of trees, namely 100 trees. And then we specify the -- imbalance option. So note that we do not specify a value for this option. We're simply using the -- imbalance, And simply using the -- imbalance option tells Skytree that we would like to treat the dataset as an imbalanced dataset and just do the necessary adjustments. The next option is something we will talk more about in a later session, but just to give a quick summary for now, Skytree by default uses a type of regularization with gradient boosted tree models. And that regularization cannot be used simultaneously with the imbalance option, so we just turn it off here. We then specify the testing file and the output files for the model that we want to write out and the predicted probabilities and labels. So with this one, Skytree will create a model using the training set and by doing the necessary adjustments for the imbalance in the data, and then use that model to make predictions on the test set and write out those predictions and also write out the model obtained. So how does Skytree take the imbalance into account? With the simplest approach that we're showing on this slide, Skytree randomly downsamples the more frequent class so that it has the same number of data points as the minority class, and then trains a gradient boosted tree model on the resulting dataset. Of course, a gradient boosted tree trained on the downsampled version of the original dataset makes distorted predictions for the two classes, and Skytree actually applies a correction to the estimated probabilities for this downsampling. So the probabilities reported for the two classes are adjusted versions of the probabilities predicted by the base gradient boosted tree model trained on the sampled version of the dataset. So let's give this a run. So let's take a look at the probabilities that were written out by this training run. I'm actually going to use the Linux paste command to print out the probabilities side by side with the previous model that we trained, which also used the 100 trees, but it did not use the imbalance option. So we see that the probabilities have changed between the two runs. By default, the imbalance option downsamples the majority class to make the two classes of equal size, and then performs the training. Skytree also provides the user with more detailed control over the treatment of imbalance, and this is done by using the imbalance scale and the sampling ratio options. The sampling ratio option allows the user to specify specific sampling ratios for the two classes. For example, if you want to downsample the majority class by a factor of 100 and upsample the minority class using sampling with replacement by a factor of 2, you would specify the appropriate sampling ratios using this option, the sampling ratio option. The imbalance scale option is a simplified version of sampling ratio. It always samples the two classes to make them of equal size, but it also allows upsampling of the minority class. For instance, if you want to sample the two classes so that they both end up having twice the number of examples in the original minority sample, you would set the imbalance scale option to 2. The imbalance scale and sampling ratio options are both tunable, so if you specify multiple values for these options, and if you use a tuning setting such as a holdout ratio or a number of cross-validation folds, Skytree will try the values that you specify for the imbalance scale or the sampling ratio and pick the best one. Let's next give a run for tuning over the imbalance scale. We will begin by specifying the GBT option, then the file names for the training data and training labels as usual, and use a fixed number of trees. To do the evaluation for the tuning runs, we will use cross-validation this time. So previously we used the holdout ratio option to pick a random holdout set for evaluation, but this time we're specifying the num folds option to use 3-fold cross-validation. We then specify the imbalance option as in the previous one, but this time in addition we specify a range of imbalance scale. So our imbalance scales are going to start at 0.5 and they will go up to 2 with steps of 0.5. For each value of this parameter, Skytree will sample the two classes accordingly. For example, for an imbalance scale of 1.5, the majority class will be downsampled and the minority class will be upsampled with replacement so that they both have the same number of points, which will be 1.5 times the number of points in the original minority class. Once again, we turn off the regularization option, which is on by default, and this option can't be used simultaneously with the imbalance option or the sampling ratio option. We will write our tuning results to a file. We will also use the Linux T command to both see the output from Skytree and have it written to a file. For this particular run, we're not writing out the final model and we're not making any predictions on a test set. So let's give this a run. With this run, we wrote out two files, the log file and the tuning results file. So let's first open the log file and take a look. We see that the imbalance scale values that we picked are identified at the beginning of the log file. And right after that, we see that those values are represented in terms of sampling ratios. For example, an imbalance scale of 2 corresponds to upsampling the minority class to twice its size, and downsampling the majority class to about 63% of its original size. Of course, this number is specific to this particular dataset. In general, the sampling ratio of the majority class will be chosen to make the samples for the two classes of equal size. We then see the progress for the tuning runs. Because we specified threefold cross-validation, each parameter setting is tried 3 times, once for each fold. After the progress information, we see the best tuning results for various criteria. So let's focus on the section for accuracy. We see the best accuracy value obtained and the corresponding parameter values. So in this run, we tuned over the imbalance scale parameter, and the best configuration that was found is represented in terms of the corresponding sampling ratios. We specified the number of trees to be 100 in this run, but since on the way to building 100 trees, one first has to build 10, 20, 30 trees, etc. Checking the accuracy of those particular numbers of trees doesn't come at a significant cost. So Skytree by default tried those values too, and we see that some of the model configurations in the list actually have 70, 80, or 90 trees. A random forest is a predictive model that consists of a collection of tree models, and each tree in a random forest is trained on a different sample from the original dataset. And actually a similar approach can be applied to all kinds of learners. One can train multiple versions of a given model using different samples and combine the outputs to make a final prediction. This is actually called bagging, and random forests are actually slightly different from this. There is one additional tweak on top of this idea, namely dimension sampling. Skytree's ensemble gradient boosted tree models apply these ideas to gradient boosted trees. So when you use the -- ensemble size option while using the gradient boosted tree module, GBT module of Skytree, Skytree trains multiple GBTs using samples from the original dataset, and can also possibly do dimension sampling, and finally combines the GBT models to obtain the final model. So we find that using the Ensemble GBT option together with imbalance handling can significantly boost the accuracy for imbalanced datasets, and it can actually help for non-imbalanced datasets as well. So this is a useful option to know about. Here's an example command that uses the Ensemble GBT capability of Skytree. As usual, we start by specifying the GBT option and the file names for the training data, and we specify a holdout ratio to do the tuning. So in this run, we then specify the ensemble size. This turns on the Ensemble GBT training, and Skytree tries out different sizes for the ensemble specified with this option. For this particular example, we will try ensembles that consist of 1, 3, 5, 7, and 9 GBT models. We're also using the num dimensions options here. This option can be used with Ensemble GBTs and also with random forests, and it has a similar effect in the two cases. So for each split in a tree, Skytree will consider only a randomly selected subset of all the possible dimensions, and this option determines the number of dimensions to consider. So for this particular run, we're going to consider 2, 3, and 4 dimensions at each split. And finally, we specify the file to write the tuning results, and also use the Linux t command to write the log to a file while it also shows up on the terminal. So let's open the tuning results file and take a look. We see that many of the variables have fixed values through all the runs. For example, we had chosen the number of trees to be 25, and we see that that's fixed through all the runs. We did tune over the ensemble size option, and we see that that varies from 1 to 9 with steps of 2, just as we specified. And we had also chosen to tune over the num_dims, the number of dimensions to sample, and we see that the values for that variable are 2, 3, and 4. And let's next open the log file and take a look at that too. So near the beginning of the run, we see that the ensemble size option shows the values that we had picked, 1, 3, 5, 7, and 9. And we also see the number of dimensions that we had picked, 2, 3, and 4. And as we scroll down, we see the results for various different measures of accuracy. And let's look at the one for classification accuracy, meaning the fraction of correct answers. And we see that the model with the best accuracy has an accuracy of 83%. And that corresponds to an ensemble size of 9 and the number of dimensions 4. So we tuned over different ensembles of GBTs, and the ensemble that gives the best accuracy consists of 9 different GBT models combined together. Parameter tuning is a time-consuming task in machine learning. If you want to try 10 different parameter settings for 3 variables, that makes a total of 1,000 different combinations to try. And with an increasing number of interdependent options, things only get harder. Data scientists use a combination of grid searches and their intuition to figure out the best combinations for their models, but this is a tedious task. Skytree has a smart search option that automatically explores the parameter space and zooms into promising regions to optimize the notion of accuracy chosen by the user. To turn on the smart search, you just need to use the -- smart search option, and you need to specify the desired number of iterations by using the smart search iterations option. Turning on smart search in this way will trigger a search over all available parameters, but sometimes you may want to restrict your search by fixing the values of some of the parameters or by choosing upper or lower bounds for certain parameters. So to use a fixed value of a parameter, you simply use the option for that parameter as if you were choosing a value in the regular non-smart search runs. And to specify upper or lower bounds, you just need to use a colon notation. A colon followed by a value specifies an upper bound. A value specified by a colon specifies a lower bound, and 2 values separated by a colon specify a lower bound and an upper bound simultaneously. Here's a simple smart search example. In this one, we first specify the GBT option and the training files, and choose a holdout ratio. After that, we turn on the smart search option and specify the number of iterations we would like to use. In this particular run, we're using 10 iterations. We then specify our objective for optimization by using the testing objective option. And for this particular run, we would like to maximize the classification accuracy, so we use the accuracy option. And we then specify the upper and lower bounds for the number of trees. We would like to restrict the smart search over the number of trees to a minimum value of 2 trees and a maximum value of 200 trees. This is not required, but it's in general a good idea to specify at least some upper bound for the number of trees, since very large numbers of trees can result in a run that takes too long. And finally, we specify the file to write out the tuning results and also the file to write out the best model found during the smart search. Here's the smart search run. We see that some iterations take longer than others because perhaps they consist of a larger number of trees. And Skytree just goes over all the iterations that we had specified, which was 10 iterations in this case. And once it's finished, it records the model with the best accuracy. So let's open the tuning results and take a look now. So we see that a very wide range of values have been tried for many of the parameters. So we're not just fixing a bunch of parameters and looping over values for the others, but Skytree is really exploring the whole parameter space. So we could have fixed some of the parameters if we wanted to, but that's just an option. And let's take a quick look at the log file as well. Let's scroll all the way down and look at the section titled Best Tuning Results for Accuracy. We see the best accuracy value here, and we also see the parameters for that best accuracy value. So this tells us that the number of trees for the best accuracy is 77, and maximum splits is 7, and minimum node weight and learning rate. All these things that Skytree really explored over. So in this particular run, we had 10 iterations, but in general, it's a good idea to have more than that. You will not get a good convergence with just 10 iterations, but we have found that about 100 iterations allow you to get a really good model in general. With gradient boosted tree models, there are ways to assess how important each variable or each column in the data is for predicting the output. One way to quantify this is to look at all the splits that use a particular variable in all the trees of the model and calculate how much those splits reduce the so-called impurity. And a weighted sum of all these impurity reductions give a measure of the importance of that particular variable. So with Skytree, to write out the variable importances, we use the variable importances out option and simply specify a file name. The file written out will contain one line for each variable, and those lines will contain the importances for the corresponding variables. The values are normalized so that the most important variable gets a value of 100. And the ordering of the variables is as in the Skytree data file used with the modeling run. Here's a run that first tunes a model, trying 4 different values for the number of trees and a 30% holdout set, and then writes out the best model found and also the variable importances for that best model. So we simply specify the file where we want to write out the variable importances, and that triggers Skytree to calculate those variable importances and write them out to that file. So here's the variable importances run. So let's skip the log file and the tuning results file this time and just open the variable importances file. As you can see, this is a really simple one-column file, and the numbers correspond to the importances of each one of the corresponding variables. So the ordering of the rows is the same as the ordering of the variables in the original data file that we used to train this model, the Skytree data file. So there's one variable that has an importance of 100. So this is how the normalization is done. The most important variable gets an importance value of 100. And all the other variables are less than or equal to this importance value. And this can give great insights about the data if only a few of the variables have importance values that are appreciable, and if many of the others are just very close to 0, have low values. Then we can start thinking about why those particular variables have such a strong predictive behavior. So here's a quick summary of what we went through in this training. We saw how to train and tune models using the Skytree GBT module. We saw how to use a holdout set or how to do cross-validation by Skytree. We saw how to handle imbalanced datasets using the imbalance option, or to have finer grain control over the imbalance handling, how to use the imbalance scale and sampling ratio options. We saw how to train and tune an ensemble of GBTs with Skytree using the ensemble size option. And optionally, we saw that we could also specify the num dimensions option. And we learned how to do smart search over all the parameters using the Skytree smart search capability. And we saw that it's possible to do a more restricted smart search by specifying fixed values or bounds for certain parameters. And finally, we show how to obtain the importance of each of the variables in the data using the variable importances out option. With this knowledge, you can go ahead and build very accurate gradient push-to tree models with Skytree. But there are many other options with Skytree GBT module, which you can read about in the user guide.